Okay, first I would like to thank very much the organizers for inviting me and giving me the opportunity to present our results here. So today I'm going to show you new data that we have obtained in a recently discovered stoichiometric iron-based superconductors, where we have tried to get new insight about the gap structure and the pinning mechanism in this material. Well, yesterday we already saw some talk, the Kontikowski talk, about iron-based superconductors. So this material was discovered in 2008, and where it was kind of surprising to have such a high critical temperature in materials that contain iron, because superconductivity is supposed to compete with magnetism. So soon after, several families of this material started to appear, and here I show you the crystalline structure of some of them. All of them have in common this this iron arsenic plane, which is supposed to be very important to the metallic, but also for the superconducting properties. Well, these are multi-band systems, which make them very interesting. Indeed, so there are several bands that cross the Fermi surface. Typically, there are two or three whole bands crossing the Fermi surface, the Fermi energy at the center of the Brillouin zone, and one or two electron bands crossing the Fermi surface close to the border of the Brillouin zone. So these produce this kind of Fermi surfaces, which has a quasi-two-dimensional character. So different pairing symmetries has been discussed in these materials. Most of them involve the change of the sign of the superconducting gap over the Fermi surface. And today there is some consensus that in most of these materials, superconductivity is consistent with S plus minus pairing, which means that we have an open energy gap over the whole Fermi surface, but still it changes sign in different parts of the Fermi surface. We also saw this phase diagram yesterday. So this is a schematic phase diagram for this kind of materials. So the parent compounds are antiferromagnetic at low temperatures. They show this kind of stripe-like antiferromagnetic order. They also have a orthorhombic crystalline structure and a sort of electronic order, which is named nematic in analogy with liquid crystals. So when we dope these systems, superconductivity emerges, and often with the maximum critical temperature, with the highest critical temperature, close to the point where this order goes to zero at zero temperature. And that's why often we talk about quantum critical points and the effect of quantum criticality in these materials. Although I have said that most of the highest critical temperature appears in dope compound, there are also stoichiometric iron-based superconductors which show superconductivity. And here I show you a few examples, but more often they show very low critical temperatures. So it would be ideal to have the possibility to study one stoichiometric compound with high critical temperature to investigate the intrinsic properties that lead to the high critical temperature in these materials. The vortex lattice has been also studied in these materials, and here I show different STM images of the vortex lattice made in different materials and by different groups. The common feature is that the vortex lattice often appear very disordered, but still we don't have a clear picture, a clear correlation between the disorder in the vortex lattice and the pinning landscape. So again, in these materials, the vortex lattice has been studied in presence of substitutional disorder in dope compound. So again, it would be nice to try to study the disorder in the vortex lattice in an intrinsic, in a stoichiometric material in absence of this substitutional disorder. So this is the main motivation of the talk. So here I will present new data in a recently discovered stoichiometric superconductor, calcium, potassium, iron 4, arsenic 4, which was recently discovered. It has the critical temperature of 35 Kelvin, which is the highest critical temperature among the stoichiometric compound. So it was first synthesized last year, first in polycrystalline form, and a few months later in single crystal form by the group of Paul Canfin. Well, we have studied this material using a scanning tunneling microscopy, and before I show you the data, I'm going to briefly introduce the experimental technique and also the facilities that we have in Madrid. Well, as we also saw yesterday, a scanning tunneling microscopy, when it's operated at very low temperatures, allows to measure directly the local superconducting density of states. So it allows also to measure the spatial variation of the density of a state, and this gives the possibility to directly image the vortex lattice. Well, in Madrid, we have different dilution refrigerator STM. So we can cool down to 100 millikelvin and apply magnetic field up to 17 Tesla. So they have an energy resolution of 15 microelectron volts, which has been tested using measuring clean spectra in low DC superconductors, such as aluminum. Well, our STM has a mechanical pooling system that allows to change the relative position between the tip and the sample at distance of a macroscopic distance of a few millimeters with a precision of some tens of nanometers. And this is useful, for instance, to be able to prepare the tip in situ and at low temperatures. It also allows us to clip the sample in situ at very low temperatures. We use this mechanism to clip the sample, producing very flat and large atomically flat surfaces. And here I show you an example of one of the surfaces produced after this cleaving at 100 millikelvin. But we have already used this method to clip many systems, many crystals. Well, one important point that I want to stress, and I will use later in the talk, is that in an STM, the Z-axis transport is not the only contribution to the tunneling current. So due to the small lateral size of the tip, quasi-particles are injected in all directions. So this makes that all the parts of the Fermi surface contribute to the tunneling current with a significant weight. So this is not important in the case of isotropic superconductors, where we have a constant value of the superconducting gap over the Fermi surface, but it's indeed very important in an isotropic superconductors, where we may have a distribution of gap over the Fermi surface. So just by looking at the difference in the shape of the conductance, we can get information, the tunneling conductance, we can get information about the distribution of gap in the Fermi surface. Well, there are many materials where multi-gap structure has been observed. Maybe the most prototypical is the result in MGB2, where two clear peaks appear in the tunneling conductance due to the two-gap structure of this material. Well, with the STM, not only we can measure we can get information in the real space, but also in the reciprocal space. And we also saw that, some data yesterday, using the quasi-particle interference imaging technique. So using this technique, essentially we obtain in conductance maps a standing wave produced by scattering of electrons in defects, and studying the wave vectors and its dependence with the energy, we can reproduce the electronic band dispersion. This is quite useful to study metals, but also superconductors, because we can directly see how the superconducting gap opens in the band structure. Also, we saw yesterday that this technique is particularly useful to study topological materials. And we saw some examples yesterday. And here I want to show you some preliminary results that we have obtained in the type 2 by semimetal tungsten ditelluride, where we have obtained information not only from the surface band structure, but also from the bulk band structure. So essentially, in this material, we have a bulk electronic structure when we find some points. And in the surface, we have the projection of these points, which are connected by open Fermi surface, which is known as Fermi arcs. So we have made a QPI study in this material. In the top part, I show you the band structure for the bulk, and in the lower part, the band structure for the surface. So in the bulk, calculations show that we should see two small hole pockets in blue and two small electron pockets in yellow. in the surface band structure, we observe these two Fermi arcs, one below the Fermi surface and one above the Fermi level, one below the Fermi level and one above the Fermi level. The one below by the Fermi level has been already observed by ARPES data, but as we know, ARPES data have no access to the empty states. So while we have made a QPI study of this material, this is a topographic image that we obtained after cleaving the sample with the method that I showed you before. So we can directly see these atomic chains that are expected from the crystalline structure. So when we do an larger scale imaging, we can also observe defects on the surface that can be seen in the bottom image. So essentially, we find two types of defects, one which are missing atoms, which are there, and other which are like atoms. So we have seen the effect of both types of defects. When we look at the QPI signal produced by these holes in the lower part corner of the image, essentially what we find is three QPI vectors which are consistent, which give information of the bulk band structure. So we have started a collaboration with the group of Professor Arita in Recon. They have made band structure calculation, and they have also calculated the constant energy contours as a function of the energy in the energy range that we have measured. And essentially, we can explain the energy dependence of the QPI vector that we observe from the bulk band structure. Well, when we look at the QPI signal produced by the other type of defects, essentially what we obtain is information from the topological state at the surface. So the QPI signal expected from one of these Fermi arcs are this feature with an 8 shape. So when we look at the QPI signal, we find the appearance, I don't know if it is clear here in the screen, but you can see the appearance of this 8 shape feature in the Fourier transform at an energy below 50 and 60 millielectron volts. This is a clear signature of the presence of the Fermi arcs, and they appear at the energy where band structure predict the appearance of this Fermi arc, and also at the position of the projection of the Weyl point on the surface. Well, just to finish with this experimental part, I wanted to show you we have been working in setting up a new low vibration lab with floating floor. Here I show you a picture that was taken a few weeks ago. The lab is supposed to be fully available in a couple of weeks. And here we are going to set up a very high magnetic field STM to do STM measurement up to 22 Tesla using superconducting magnets and about 30 Tesla using resisting magnet in international high magnetic field facilities. We also have started to grow some simple single crystal of iron-based superconductors. Well, now I go to the main topic of the talk. So as I told you, we wanted to study this recently discovered superconductor. It has the highest critical field, the highest critical temperature among the stoichiometric superconductor, which is of 35 Kelvin. It has been measuring by different microscopic techniques. So the temperature dependence of the resistivity shows that there is no sign of either structural or magnetic transition in this compound. So we don't have substitutional disorder, and we also don't have this disorder produced by structural domains in this sample. The upper critical field is very high, it's isotropic, and it's very high at low temperature, it's above 70 Tesla. Here I show you a typical topographic image that we obtain after cleaving the sample at low temperatures. The image on the right is the whole scanning window. It says image of 2 microns with a corrugation of less than 2 nanometers. So it's really flat. It's atomically flat. So when we zoom up, we see 2 different kinds of surfaces, which essentially consist of missing rows and remaining rows, most likely of calcium or potassium atoms. When we look at the density of a state at low temperatures, we see that the density of a state shows the presence of 2 different superconducting gaps. It can be also observed in the gap distribution shown on the right. So we always see two peaks in the gap distribution, around 3 millielectron volts and 7 millielectron volts, although the relative weight between the two gaps changes a bit with the position. We have made a joint work, collaboration work with a group of Proshorov at Ames. They have measured on the same samples the magnetic penetration depth. And from the temperature dependence of the superfluid density, they also need for fit their data the presence of two superconducting gaps with similar values to those obtained with STM. From the low temperature dependence of the London penetration depth, they find that the superconductivity in this material is consistent with S plus minus pairing. We also, ARPES data has been made in the same samples by the group of Kaminsky. They have found 3 hole pockets around the gamma point and 2 electron pockets around the Fermi, the corner of the brilliant zone. The inner gamma hole pocket, alpha, disappear close to the Fermi level, and they have found an open superconducting gap over the whole Fermi surface, also with 2 different values of the superconducting gap. And these 2 values are well separated in the Fermi surface, which also favor the appearance of S plus minus superconductivity. We have made the QPI study in this sample. As I mentioned before, we first look at the large atomically flat region. Then we make conductance maps at different energies, and we analyze the quasi-particles vectors that appear in the Fourier transform. Here I show you the different images that we obtain as a function of energy between minus 13 millielectron volts and 13 millielectron volts, and the corresponding Fourier transform where we can identify a QPI vector that increases when we increase the energy. You also can note that at the Fermi level, the signal disappears due to the opening of the superconducting gap. So when we plot the QPI vector, we find that this scattering vector is consistent with a scattering vector between the outer and middle hole pockets obtained by ARPES data. And above the Fermi level, where ARPES data have no resolution, essentially we find that this QPI vector increases, and due to the fact that we are reaching the top of the middle band. As we can see, we lost the signal close to the Fermi level due to the opening of the superconducting gap. In this graph, we have plotted the radial average conductance at the QPI vector as a function of energy, and we can reproduce the 2-gap structure that we have seen in the tunneling data, exactly with the same values. You may note that the signal doesn't go to 0 at the Fermi level, and I discuss in a moment why. When we apply magnetic field, we have seen the vortex lattice as a function of the magnetic field from 1 Tesla up to 8 Tesla. The vortex lattice has hexagonal symmetry, as can be seen from the autocorrelation function images. The vortex lattice is quite disordered. The hexagonal order disappears after a few lattice spacing, and the intervortex distance behaves with the magnetic field as expected for a hexagonal lattice. We have also analyzed in more detail the vortex core. The vortex core have a round shape, which indicate that there is not in plane anisotropy in this material. When we look at the evolution of the superconducting density of a state when going from inside to outside the vortex core, we find the presence of a localized state at a positive bias at the center of the vortex core that evolved to the 2-gap structure that we observe outside the vortex. So as we know, the lowest energy localized state appear at the energy of 2 delta square over the Fermi energy. In conventional superconductor, this value is too small, it's practically 0. But in superconductor close to the quantum limit, where the Fermi energy can be large, can be small, and the superconducting gap can be large, we can see localized state at non-zero energy. This has been previously observed in different superconductors, in mid-type superconductors. They have seen the presence of this localized state and non-zero energies. But in most cases, they appear at negative energies, and we find this localized state at positive energies. One possible explanation for this is that, as I mentioned before, ARPES data have seen that this gamma band, this alpha band, disappear very close to the Fermi energy, and this can produce an electron-hole asymmetry that can be influence the shape of the core state in this material. Was just back to the fact that this signal is non-zero at zero energy, and the reason why it's easy, we can see it when we look at the conductance maps at the Fermi level. We see that the conductance, the density of a state is not zero in every place. We find some places where the conductance is different from zero. And we understand why when we look at regions with a relatively large amount of disorder. We found that close to steps or small holes, close to defects, we have an increase in the density of a state at zero bias. We have pair breaking. So this is consistent with the fact that most likely we have an S plus minus superconductor. So these defects most likely are producing scattering between parts of the Fermi surface when the gap changes sign. So I don't have time to enter in details, but we have also observed that the defects producing the QPI signal is different from the defects producing the pair breaking. Then we have studied the effect of these pair breaking effects in the vortex lattice, and to do that we have again choose a region with a large amount of defects, these steps, and look what happened with the vortex lattice at two different fields, 2 Tesla and 3 Tesla. So we can see that these defects produce an enhancement of the density of a state, so they produce pair breaking as we observe in zero field. And when we look at the position of the vortices, we find that some vortices are placed on top of this defect. And the vortices which are there doesn't change their position when we change the magnetic field. Whereas the vortices which are between this defect change their position when we increase the magnetic field. This indicates that the vortices are strongly pinned to these pair breaking defects. And probably these pair breaking defects are the more important contribution to the pinning in these samples. We also have analyzed the images where we don't have the limit of this individual pinning limit, but collective pinning in a region where the disorder is more homogeneously distributed. And we have found very disordered vortex lattice. To quantify the disorder in the vortex lattice, we have calculated the positional correlation function. Essentially, this function is constant and is equal to 1 and independent of the distance for a perfect hexagonal lattice, and its value decays with the distance when we introduce some defects. So when we calculate this positional correlation function, we find that it decays exponentially, indicating that we have a short-range hexagonal order in the lattice. We have also calculated the relative displacement correlator, obtaining a arcing distance of a few lattice spacing for this material. More detailed characterization of the disorder has been made by Jose Benito and can be seen in his poster. Well, just to finish, I conclude. So in this stoichiometric material with very high TC, we have found multi-gap superconductivity, which is consistent with S plus minus pairing. And we have found that the main contribution to the pinning, the intrinsic pinning in this material in absence of substitutional disorder, is the pair breaking defects. Just to finish, I want to acknowledge the people that has been involved in this work. The experiment on the iron-based superconductor has been made by Anton Fente, who just finished his PhD, and the experiment on the tungsten ditelluride has been made by Francisco Martin, all in collaboration with Herman Suderov and with the people from Ames. Thank you very much for your attention.